Yeah. 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 I will begin with a word of prayer. So, dear Father, we thank you for this day. I thank you for students. Just ask you to bless our time together, Lord. In your name I pray. Amen. Yeah. So the thing is, basically just basically just. I mean, it's the reason I don't ask this to linear is very simple. It's because it's not really a linear problem. It's a factoring problem. See, because the whole question is, what does that condition mean? X cubed minus y cubed. Well, that's equal to x minus y times what? Plus xy plus y squared, right? So if you study this quadratic, I believe you can see in the case of x and y being real variables, it has no zeros. Therefore, the solution set to x cubed minus y cubed is just the set x equals to y, which of course is a subspace of R2. However, in the case of complex variables, there is more in here. You can find different lines which take this as a zero. So like the solution set, I think is, I haven't studied it enough, I'm not absolutely sure, but I think the solution set's like 3 lines or something like that. Maybe it's more, but it's lines. If I do what? Divide by y cubed. What do you mean divide by y cubed? Oh, yeah, thank you. So so you're saying you're looking for really x over y cubed equals to 1. Supposing y is non-zero. Of course, if y is equal to 0, that's... But yeah, there are three different solutions to that. One of them being x equal to y, and the other ones being related to third roots of unities for slope. Yeah. So if you take if you take things on the different lines corresponding to the slopes of the root of unity, and you add 2 of those things together, they're not in the subspace. It's like a collection of 3 lines. That's not a subspace. That is what I call a hard linear algebra question, right? Yeah, I think so. I mean, it's not, what makes it hard isn't really linear algebra, is it? It's algebra. Yeah. This is not my problem. Dr. Smith gave that one to me. I was very happy. Very much outside of the... They were completely surprised by it. But what I like about it is really, if you take a hard look at the math we've been doing in 422, that's a reasonable question. It's not outside the realm of possibility that somebody could answer it. In fact, I think one of them did find the counterexample that I'm talking about. All right, so we're talking about covering spaces. And I should probably try to prove some of these theorems foolishly. Actually, I'll ask you guys, what's your preference? See me try to foolishly prove theorems, or see me try to foolishly state new theorems? State new theorems? All right. You are wise. Where did we get to? We talked about the path lifting theorem, right? What did the path lifting theorem say? Yeah, I guess I should talk about the... right, here's the, maybe the better picture. E, the covering space, right? Down here, the space which is being covered, X, right? And then there's some mapping P. And if we take a path well, the thing we were most interested in, of course, was if we took a loop here, right? If we took a loop there, then it lifts to not a loop upstairs, but the thing is, let's see here, I had to remember the fiber over x naught, right? So these P inverse of x naught is this discrete set of points, one in each, what were these called? The sheets of the covering, right? Sheets of the covering space. And oh man, now I'm really confused how to. Maybe is my picture still the wrong picture? Are the sheets disconnected? Are they globally disconnected, or are they just? So now I'm having trouble thinking of how to draw my picture. I'm forgetting something, guys. What's that? The helix? Yeah. Well, look at the look at the helix, right? It's the maybe a kind of yeah. Okay. Maybe this is an okay picture. Something like if you understand my picture. So what I'm saying is that so like there is the sheets are not, the covering space is more than the sheets, right? Sheets are with respect to an open neighborhood of the point in question. So like if I pick something like this, right? Say U, then P inverse of U, not that P inverse is a map, right? It's multiply valued, so it's not a map. But these are the sheets. So the sheets of a given local neighborhood in the base space, those are disjoint. But that's not to say that the covering space is disconnected. The covering space itself is not disconnected, right? I mean, like if you read the theorems I'm about to state, actually say something like the covering space is simply connected, or something like that, if I recall correctly. And so that's important because I was having trouble like envisioning in my mind, we're lifting this loop, right? And the thing was, we said it lifts to something that's not a loop, necessarily, all right? But the deal with the lifting, the deal with the lifting of the loop is that the basic idea was that a loop lifts such that its terminal point, points separate, possibly, but they just lie on different sheets. And let's above x naught, you know. So what I'm trying to say is x naught is equal to alpha of 0 is equal to alpha of 1 is equal to x naught, right? The loop begins at x naught. It's a loop based at x naught, okay? So the loop begins and ends at x naught. But when we lift that loop up to the covering space, all right, then it could be something like it starts, let me draw it in green. Like something's happening beyond just the sheets, right? Because we're still the wrong color. It's something like this, right? Oops. I don't know how to draw this. It could be like that, you know? This loop could lift to something like that. But it has to be that the terminal points of the lift, this is the worst. I will call you back. Vietnamese. That was Min. So. I'm giving a talk, and I think he wants me to tell him what the abstract is. So I probably should do that. Okay. So again, the terminal points of the lift have to lie on the fiber over the point in the space which is being covered. All right, that's the big observation. Let me try to state the theorems again here without stating everything. I mean, this is what he gets to on page 128. The terminal point all right, I probably need to go through this discussion. I think this is the discussion we kind of glossed over last time. We should start here. So he says, this is on page 127, okay, so I'll start here. Try to start here anyway. Now, let E comma E and X comma B be pointed spaces. You know, the way that sounds to the uninitiated, like to the naive listener to topology, you'd have a really wrong idea in your mind's eye what pointed space means. What would you think of if you hadn't had this course and heard the term pointed space? You'd probably think it's pointy, right? But this is just saying that there's a point in this space which has been singled out. Somehow you can do that. How could you not do that, right? But anyway, there it is. And I think it's context that would not allow you to do that with clarity. Okay, then let P from EE to XB be what? Be a covering map. Oh, Jonathan, I keep forgetting. My brother sent me a link to a MathStack Exchange question about your question, about the possibility of an infinite product, and the answer seems to be no. But it's at least no in the product topology. I'm not sure about the box topology. It's something that it's unpleasant. Yeah. I'll try to send you, if I don't send you that link tonight, poke me, I will send it to you. Okay. where was I? Yes, covering map. So what does that mean? Here we're assuming what? P of E equals to B, right? We're also assuming the points line up under the covering map. And he says, let gamma from 0 to 1 be a loop based at B. So at the moment, what is B in my picture? This B is my x naught, right? Let's set B equals to x naught for the sake of discussion. Hopefully I won't read 3 sentences further and have him use x naught in a different way. That would be unfortunate. I think we're okay. That's always the worst, you know? Okay, so what does this mean? Gamma of 0 equals to gamma of 1 equals to x naught, or B if you like, okay? Then what? He says, by the path lifting theorem, there exists unique alpha from 0, 1 to the covering space, all right? Such that what? Such that it starts at E. So the path lifting theorem says that if you pick a starting point up here somewhere, and you pick a path down in the base space, right? And you lift to that starting point, then that's unique. If you had 2 different paths which both lifted to the same starting point, like, you know, the lift of the path both had the same starting point, then that makes them unique. I mean, you could lift a given path to different places, but once you start it at the same, you know, sheet over a given point, then that's unique. But of course, you could lift the loop different places. You could, in principle, lift it like up there. I mean, there's different. But once you start it somewhere, that is unique, all right? And so that was the path lifting theorem, all right? That was theorem 5.2. Okay. So there exists a unique lift alpha, such as alpha 0 is E, and he says that the lift alpha need not be a loop since it need not terminate at E. However, the terminal point alpha of 1 satisfies P of alpha of 1 equals to gamma of 1. So like here, this in my picture is alpha of 0. Up here in my picture is alpha of 1. As you can see, it's not a loop, all right? Alpha of 1 is an element of the inverse image over x naught. It's in the fiber over x naught, which is just a fancy way of saying that P of alpha of 1 is equal to x naught, right? Now what he says is, suppose now that you have another loop. Suppose you have another loop in x based at B such that gamma 1 is homotopic to gamma with endpoints fixed. All right? And he says, and then he gives the homotopy here. All right, so let me draw a picture. We need another, so my current loop is gamma, right? And he says, take another loop down there. I need another color. If I can find a brown, that'd be awesome. Have I used purple yet? I haven't used purple yet, have I? So another loop, right? Gamma 1, such that gamma 1 and gamma are homotopic, all right? And then All right, what's he going to do? What are we going to do with that? He says, you guys can help me unpack this. He says, let bracket gamma sub t 0 less than t less than or equal to 1. He says that be the homotopy. Do you remember that? I don't remember that. So that gamma 0 is equal to gamma.
That's just another way that he said he would notate the
Okay. F. So that's just yet another notation for the homotopy between gamma 0 and gamma 0 being. So that says that there exists, yeah?
I think I like that more because I think the intuition is like we have this collection of different paths ranging from that first one to the second.
Right, you can almost kind of like envision it in your mind's eye that I'm not going to do it because it'll clutter my picture or something fierce, but there's like a gamma t that's a variable path between this, and you're kind of like blowing it up or out from the gamma out to the gamma 1, like that. And so starting the black being t equals to 0, the purple being t equals to 1, and there being a continuous kind of collection of paths going from one to the other, that's the homotopy. Okay, where was I? He says applying theorem 5.3, theorem 5.3 in a nutshell says that you can lift the homotopy. Theorem 5.3 says you can lift the homotopy. If you've got a homotopy down on X, you can lift it to a homotopy up on E. All right, so I guess I'll just have to, I'm sorry guys, I'm going to have to write that out. I don't see I have much choice in the matter. Theorem 5.3, it says let P E going to X be the covering map. And homotopy F, from 0, 1 cross 0, 1 to X, right? B map. And let E naught in the covering space, E, satisfy P of E naught equal to F of 0, 0. All right. Then there exists unique G 0, 1 cross 0, 1 to E such that G of 0, 0 equals to E naught. So it's not exactly a homotopy yet. I mean, a homotopy is definitely it's a continuous map from 0, 1 cross 0, 1 to X. But there are terms and conditions, right? We had those axioms for the homotopy, right? Like the, how's it go? Yeah, let's write that out. So what was it? F of Oh, gamma 0 at what? No.
Just that when t equals 0, we have the first pass, right? And then when t equals 1, we have the second pass.
So f0 of s. I mean, he's got it in z back on page 120, but the song remains the same here. F of s1 is f1 of s, and f of 1t and there's something else. Yeah, I think I'm looking on the wrong page. Come on. Yeah, I'm sorry. Yeah, exactly. Okay, so trying to think through this. If we had a homotopy, if G was a homotopy, excuse me, if F was a homotopy between gamma and gamma 1, right? What would that look like?
5.3 is more general than that.
Yes. Right. Yes. I'm just saying what happens when we apply 5.3 to a homotopy. Right? And let's be more specific. Let's apply 5.3 to the homotopy we're interested in, which is the one between gamma and gamma 1. Right? So this would be gamma 0, right? Which is just what we originally called gamma of s. This is gamma 1. And they're loops, right? They're loops. So 1t is x naught, and 0, 1 is x naught. Because every path in the homotopy begins and ends at x naught. Every path in the homotopy, the loop homotopy, is a loop beginning and ending at x naught. So what does that do to us?
The idea is that whatever that fixed point for the loop is,
Mm-hmm.
count all of the different loops.
Right.
And we fix that onto one of the sheets above it. That gives us a unique new homotopy on or a unique new collection of paths on whatever that sheet is that we pick.
So this basically starts all the lifts. I mean, the lift of any dang it. What's that? Lift of F. Yeah. Yeah, that's kind of important. Although I think, the question is, what does that mean? So this means that P composed with G is equal to F. Right. Okay. So he says, now that we have this out in front of us again, let's come back to here. So let gamma t be the homotopy such that gamma 0 equal to gamma. He says applying 5.3 to F The entire semester I met with Spencer to do advanced calculus. We met Monday, Wednesday, Friday from like 4 until 5:30, something like this. It was just him. Every day, without fail, like in the middle of our meeting, janitor would come in. Like, and we're like, yeah, we're still working. And they just, I don't know. After the 10th time they do it, you ask the question, I don't know, how do you interpret that? I don't know. I have no good answers to that. Anyway, I get distracted. F of st, gamma sub t. All right. So he says basically apply Theorem 5.3 to that homotopy, which is what I was trying to do over there, right? Already. He says then we obtain the map G, a homotopy on E, right, such that, God, look at this. Come with me. Just spranoing the board. Dang it. All right. Hence, obtain G 0, 1 squared to E, such that what? G of 0, 0 equals to E sub naught, right? And what else? Oh, there was no E sub naught here. Where'd that E sub naught come from? Oh, it's E over here. There's no E sub naught. I don't know. So I'll just... All right, anyway. And what else do we know? P of G of st is equal to what? Yeah, f of st, right. So I guess that tells us things about the homotopy. I mean, I guess the question is, does that make G a homotopy? Is G a homotopy then? Or no? G of, yeah, I don't, but maybe G isn't a homotopy, maybe that's okay. Yeah, yeah. Well, uh-huh. Right. Right. So let's see here. Let's see. I think we have enough on the. I think we have enough in front of us. We're gonna be able to process the next sentence now. So he says then the path alpha of t in E defined by. Come on. Let alpha sub t of s equal to G of st. What can we say about those? He says we claim that He says that the lift of gamma t and that alpha sub 0 is equal to alpha. What was alpha? Alpha was this unique. So let's see here. He does this, and then he makes he stakes some claims, right? He says, okay, so alpha t is lift of gamma t. All right. And what else? Alpha sub 0 is equal to alpha, which was that unique. And he also says that all of the alpha t's start, each alpha t starts at E. Okay. So how do we figure out where alpha t starts? Alpha t starts at alpha t of 0, right? So that's g of what? G of 0t, right? But then you're saying hit that with p? Of course, by the way, these E naughts can just be made into E's. We're thinking about this being E, of course, right? Don't let that be a problem. G of 0, 0 equal to E, right?
Well, I think he justifies the claim that they all start at E, but he makes a little argument right now.
Okay, so he's about to argue. He's about to explain why, right? Okay. So that currently needs explanation. How about alpha t is a lift of gamma t? Does that make sense? To see if alpha t is a lift of gamma t, we just need what? P composed with alpha t equals to gamma t. Is P of alpha sub t of s equal to gamma sub t of s? Right, it's exactly, I mean, this is P of alpha sub t of s, and this is gamma sub t of s. So it's literally what we have on the board in a different notation. So that's fine. All right. All right. All right, now he says to see this. Now we're going to try to see this, all right? How do we see this? He says, observe the map T maps to G of 0t, right? Is the unique lift to E starting at E. Unique lift to E starting at E. Starting at E. That's a comma, closed comma. Of what? Unique lift of what? Of the, oh, of course, the constant path. What else could you work with, right? Which we've called x naught, or b, depending on which equation you're looking at. So How does that help? Oh, so that,
I mean, the constant path at B is also a unique constant path. Right, because P of B equal to x0.
whoa, whoa, whoa. I'm not, start again. P of what?
I mean, the constant path at B is also a lift of a constant path at x0, right? Because P of B equal to x0 by definition. Yes. That has to be unique at 0. Yeah.
So you're saying Pacman from 0, 1 to E, defined by Pacman of whatever you want to call it. So we use an S or a T. I'll use an S. Pacman of S is equal to E for all S, right? That is the lift. This is the lift of let's say, ghost. Because if we take P of Pacman of S, we get P of E, which of course is X naught, which is equal to ghost of S for all S, which means that Pacman is the lift of ghost. But then what? Oh, but it's unique, which means what? So that means G of 0 T has to be equal to E? Well, in my current notation, what does that mean? G of 0 T is equal to what?
G of 0 t is equal to E times
Oh, Pacman T? Pacman T of 0 or Pacman?
I mean, Pacman of t. So you see they are both a path. Maybe that has the same stuff.
Hmm.
Yeah, that's just Pacman sub t of 0, right?
Pacman sub T of 0. And that's equal to,
Just Pacman sub t. Yeah, this path. What I mean is that Pacman, not like some parameters family of Pacmans. You feed the Pacman with just t.
like, of T.
Yeah.
Like that. Okay. Hence, yeah, the lift. So this, I mean, the ultimate, if I can see past my silly confusion, which I think is just silly confusion, we have shown that G of 0 T is equal to E for T between 0 and 1, right? And then he says, he looks at the map, T goes to G of 1 T, right? What's that tell him? He says, similarly, the map T maps to G of 1 T is the unique lift to E, starting at G of what? G of 1, 0 equal to alpha of 1, going back to that alpha that we constructed way back here, yeah? The alpha, which was the unique lift of gamma. So this alpha of 1, but alpha of 1 is of the constant path at B. Right, so what does that say? He says, hence, alpha of 1 is equal to G of 1t is equal to alpha sub t of 1 for 0 less than or equal to t less than or equal to 1. What's the point? He says all of the paths alpha t terminate at alpha of 1. He says we conclude that the terminal point alpha 1 is the same for all loops in the same homotopy class of gamma. That's really what we're trying to get to. All loops in the same homotopy class of gamma lift to the same endpoint well, the same, they lift to the same terminal. They lift such that their terminal points agree. Terminal points meaning the starting point all lifts to E, and the ending points all lift to alpha of 1.
So does this show us that G is a homotopy from with a collection of paths in E? So F, if we have F as a homotopy down in X,
Uh-huh.
it seems like G gives us a corresponding unique homotopy in E. As long as we choose whatever that initial point is going to be.
Yeah, I do think I think you're right. I think it does give us it gives us a homotopy, but not a homotopy of loops. It gives us a homotopy of a fixed endpoint homotopy. Right. And but that is interesting in its own right and important because it means that that is interesting. But what's really interesting here is that everything in the homotopy class of a given loop, they all lift. They all lift what? They all lift to the same sheet, right? The same sheet over the point. So you can only have, let me put this a different way, you can only have as many homotopy classes as you have sheets. And that's interesting.
What do you qualify as sheets?
A sheet is a disconnected open, it's the open neighborhoods which evenly cover, language, where's the, in my picture it's the little red circles.
And the number of sheets would be equivalent to the number of points in the fiber of any point, correct?
the number of sheets is the number of points in the fiber over any point. Yes. Right. So what we're getting to here is the following. He says, okay, so this allows us to define a function. We can define phi from pi 1 of xb to the fiber over b. Let me put an x naught there because it's just less tacky. Sorry, I like x naught for a point. See, because, and I mean, what is specifically, what is the map? What is the procedure here? How do you define this function phi? The function phi is given by, you take a loop, you take a homotopy class based at x naught, all right? And you lift it, right? There's a unique lift. Right, but the point is the representative of the homotopy class doesn't change the outcome. That's what we've proved here. Right, this is all a proof that this map is well defined, really. So you take a homotopy, take a loop, lift it, that's the map. Well, it's not just the lift of the loop, it's the endpoint of the lift of the loop that's the map. So essentially your phi of, let's say, gamma is equal to the lift of gamma evaluated at 1 in a somewhat tacky, I mean, that's what phi is. Big phi. He says, and he says, so phi of bracket gamma is the terminal point of the lift of gamma that starts at E. See the importance of E? The importance of E is it gives us a place to go. We need a place to take our base point into base space to start the paths up in the covering space. So the role, without that E, we don't have this construction either. All right. So I said these things last time, but as you can see, there's like a lot to really unpack here to understand it carefully. I'm sure I could have said it faster. If I had another half hour last time, we could have done this, right? It's taken me a while to get back to where we were. I'm sorry about that. So is Theorem 5.4, Theorem 5.4, it says that if we have P from EE to XB covering map, all right, and E simply connected. Oh, why am I working around this? Duh. We never needed that today, much less now. Sorry. E is simply connected. All right. Then phi is one-to-one correspondence with of the fundamental group pi 1 of xb and the fiber over b. And I'm sorry, this is an x naught. This is an x naught. This is an x naught. I refuse to use being x naught. There, I fixed it. Hey. All right. See, I thought we'd already shown that. But now there's a paragraph of proof. What's there to prove here? Ah. So all we've shown at the moment is that the map is what? Is well defined, right? So to show it's a one-to-one correspondence, we need to show, one-to-one and onto. So let's see here if we can think through it. If we look at phi of homotopy class gamma, let me call it gamma 1, equal to phi of homotopy class gamma 2, we'd like to show that those are equal. So yeah, we're assuming that's the context here. We're taking two homotopy classes of loops based at x naught, right? We're saying that they both are equal, that their image under this mapping phi is equal. What does that mean? Right, so if F1 is lift of gamma 1 and F2 is lift of gamma 2, then what? F1 of 1 equals to F2 of 1, yeah? I mean, that is quote unquote phi of, right? So at the moment, I'm just foolishly attempting to prove one-to-one directly from the definition of the function, right? A given problem in mathematics, how often is that successful? 50-50? Those are pretty good odds. Yeah. If we look at what he did here, well, he did do that. Well, he starts by showing it's onto, actually. So he shows it's onto. Okay, these both start at E, right? F1 of 0 equals to F2 of 0 equals to E. I mean, that we also know here by the construction where P of E is equal to X naught because we don't like B. Well, I don't like B. You may like B just fine. So what he says is alpha 0 and alpha 1 have the same terminal point so that the path I guess we should have wondered, right? We should have anticipated that something in what we're